What's so darn special about water? Okay, well, some of you claim that if you don't have water, you'll die, which is true. And we have talked about water's unique propensity for attraction. Water is only attracted to what? Two things. Self and everything else. So that's kind of special. Not all substances can say that. Water, if you recall, you've done Lewis diagrams, Lewis structures, and I know you love them and you probably miss them on a daily basis. Water, we've got oxygen, we've got hydrogen. Why are the hydrogens sticking up like two antennas rather than being straight out to the sides? Why is it bent? Two hydrogens are repelled by one another. Why is it bent? Would it help you if I did this? What are those? Those are what kind of electrons? Well, they are valence. What else about them can we identify? They are valence, which is outer shell. Are they shared? No, these are unshared pairs. So those two unshared pairs repel one another and repel the hydrogens just as if there was another little positive nucleus there. So that gives us this bent water molecule. And do you remember doing your molecular structure lab, you measured bond angles, right? You got out the protractor, you built your models, you measured the bond angles, and you probably don't remember this specific number, but I'm going to tell you that the bond angle between those two hydrogens is 104.9, and that's right out of your notes, 104.9 degrees between those two hydrogens. That's the bond angle. Okay, that's not so special. We don't really care about that. Now, let's revisit our little, If we look at that beaker, we notice we had that beaker completely full up to the absolute rim with ice and water when we started. And already some of that ice has melted, and already that water level is dropping. We are now actually a little bit below the rim here. We're not overflowing. As a matter of fact, far from overflowing, the level appears to be dropping. Does that seem right to you?
Yes.
Okay. So let me ask you this. Given any generic substance, substance X, we don't know what it is, we don't know what its name is, we don't know anything about it, other than, just like every other substance on the planet, we can have it as a solid, a liquid, or a gas. So I'm going to do substance X, solid, liquid, gas. Okay? So let me ask you this. In which of these phases of matter, that is hard to read. Okay, so we've got our substance X in solid, liquid, and gaseous form. What I want to know from you is, which of these is going to be the least dense? The gas. Okay, so this is going to be least dense. Which will be most dense? The solid. Okay. So will the liquid be more dense than the gas? Okay. Will the liquid be less dense than the solid? Okay, good. This is good. This is good science. We like this. So solids are more dense than liquids. Would you agree with this? Solids are more dense than liquids.
Not necessarily.
You guys seem to be having some second thoughts about this, some qualms, some concerns. But we know that solids are more dense than liquids, right? Most, for the same substance. So if I have solid iron floating in a bath of, well, solid iron dropped into a bath of molten iron, the solid iron will sink to the bottom. If I have a chunk of solid candle wax in a beaker of melted candle wax, the solid candle wax will sink to the bottom. Paraffin, well, it will melt, but aside from melting. Okay, if I take a chunk of solid water and drop it into a vessel of liquid water, it'll drop to the bottom, right? Oh, that's weird. That's weird. Okay, I'm going to pause while we discuss. So, a few of you are saying that you don't believe that solid water is more dense than liquid water, as evidenced by the fact that ice cubes float. As evidenced by the fact that the water level in that Erlenmeyer flask there is dropping, which would seem to indicate that maybe the ice was actually less dense than the water. It was taking up more space than the water does. So some of the hypotheses we could use to explain this. So one of you says maybe there are bubbles, air bubbles in the ice. That's what's doing it. That's what's doing it. Other ideas?
This expands more than it freezes.
Ah, so let's come back to Mickey Mouse. So here's the strange thing that happens when water freezes. The bond angle between the hydrogens increases. It's 109 degrees, which means that each water molecule takes up a little bit more space as a solid than it does as a liquid. I like to think of this as Mickey, when he gets cold, his ears go down. That's my own silly little thing. Yeah, it's a useful mnemonic. So that's the big thing about why. So solid water takes up more space than liquid water. How is this important for us? Have any of you ever been out on a frozen pond? Have any of you ever been out on a frozen lake? Okay. Well, have any of you ever driven up and seen Lake Erie when it's frozen over? You know, Lake Erie used to freeze solid every year, and I think it froze solid this year. When it does, you can drive to Canada. But here's as we're talking about in these notes, water expands on freezing. What this makes possible. So what would happen if water was more dense in the solid state than in the liquid state? What would happen to ponds as they froze? The ice would drop to the bottom. The whole thing would freeze solid. They'd never thaw out. It would be a significant... all of our global weather patterns are, in essence, based on the fact that water is of different... Yeah, the entire ocean would freeze solid. Our global climate is based on patterns of heat transfer between the oceans and the atmosphere. If solid water was more dense than liquid water, we wouldn't be having this conversation. So it's kind of a big deal. Somebody in the other class said, well, why does it do that? Why does that bond angle change? Why is it that way? The answer lies in a discipline called physical chemistry. If anybody here ends up majoring in chemistry, you will take P-Chem, as it's called. Your sister will take P-Chem. You can always tell people who are in P-Chem because they have big bald spots where they've torn their hair out. P-Chem is the meeting of physics and chemistry, so it's applying physics and all the force stuff that you know at an atomic level, and it's apparently a nightmare. That's where the answer lies to why this happens. I'm not qualified to give it to you. But, you know, there is an answer. I can't explain it. I did not. Okay, now, so water's got that unique characteristic. It expands when it freezes, which is real handy for us. The other important things about water, it's got a really unusually high molar heat of vaporization. That 40.79 kilojoules per mole is high for most substances. And that's because, if you remember, water has got this little thing going on where Mickey's ears are positive, Mickey's chin is negative. There are areas of partial charge on this molecule. What do we call a molecule with areas of partial charge? Polar. So we have these dipole attractions in a vat of water. Every little Mickey is attracted to every other little Mickey, chins to ears and ears to chins. So all those molecules have got these strong forces of attraction between them. You've also got hydrogen bonding. You've got multiple things going on. And that means that they're really cohesive. This is the whole attracted to themselves. Water's attracted to itself. It's got those incredibly strong internal forces of attraction. And that's what gives it the unusually high molar heat of vaporization. It's got a high specific heat capacity, is something we'll talk about a little bit later, which is it takes a lot of energy to get water to change its temperature. Okay? That's it for the notes. Some people had a question about number 24 in the homework, so let's briefly address that. in number 24, they are asking you to compare the number of molecules in a given volume of ice to the number of molecules in that same volume of water. I believe it's 5.0 cubic centimeters, correct? Okay, if you look on page 385 in your book, you will find densities for liquid water and a density for ice, for solid water. Density of liquid water, now they give you 0.99984 something. I'm okay if you go with 1.0 grams per cubic centimeter. Density of water is 1. The density of ice is given here as 0.917 grams per cubic centimeter. So all you're being asked to do initially is to set up a factor. You're going to set up 2 factor labels and use the numbers you get to compare things. So if we're starting off with 5.0 cubic centimeters of ice, we know that every 1 cubic centimeter of ice has a mass of 0.917 grams. And we know that every 18.02 grams of any form of water is 1 mole. And we know that 1 mole has got 6.022 times 10 to the 23rd molecules. Okay? That's going to get you the number of molecules in that chunk of ice. You can do the same exact problem for the liquid water, and then you've got 2 numbers that you can work with and compare.